Hi and welcome back to another lesson in the physics video series. Today we will be discussing circular motion. There are four basic centripetal force problem types: rock on a string, moon and a planet, car on a curve, and sometimes a deflected ion beam. When an object moves in a circle, it obeys a particular set of laws, and we're going to discuss those now. Okay, let's get started. So here we have a perfect circle, and an object in this case will be moving at a constant speed around this circle. And so we have a perfect circle in which an object moves around, circulates at a constant speed. The constant speed part is very important because it allows us to just focus on the acceleration and forces that keep the object in the circle. While it is fairly difficult to derive the equations for this particular concept, this simple diagram should do enough to show us that if an object is circulating and it is at a particular place, it has a tangential velocity pointing in a certain direction. And just a moment after is in a new place, that tangential velocity changes to a new angle. And in doing that, it has a delta V, and the delta V points down towards the center. And we know that acceleration can occur to a change of speed either in its actual magnitude or its direction. And since we have two different directions here, that counts for the change that creates acceleration. Ultimately, we want to know, why does an object that moves in a circle have an acceleration pointed to the center as well as a force pulling it to the center, which will be called centripetal force. We are going to be interested in applying equations 17 and 18 to all kinds of centripetal force and centripetal acceleration problems. This, of course, is page 6 of the reference table. Let's talk about centripetal force. Centripetal force is the inward pull that keeps the object revolving around the center. If you break down the word centripetal, it literally means center-footed force. Of course, when we first encounter this, it's a bit ambiguous, and we wonder, how do they come up with this term? You could see that this cool game of playing airplane requires you to spin the kid in a circle, and of course, your foot is at the center of that circle. If you could extend this picture down, his arms are bent. He has to pull in to the center, and of course, he has to bend his knees in order to give himself the leverage that he needs. His feet are at the center of this circle. That is what center-footed force means. He is pulling to the middle, and he's spinning the boy in a circle. Classic game, everybody loves it. When an object is spinning in a circle, it is being pulled towards the center. It's also accelerating to the center because each one of these velocity vectors, which is tangent to the circle at the point at which it meets it, changes its angle or position, and therefore that change of the speed produces an acceleration, and it points towards the center, the same way as the force does. So centripetal force and centripetal acceleration point towards the center. Acceleration is a change of speed with relationship to time, and the vector acceleration is a change of velocity with respect to time. If you keep the magnitude of the velocity the same, so it has an average speed, but you continuously change the direction, you thereby produce an acceleration. Since we know that F equals ma, then centripetal force, F sub c, equals m times a sub c. And so what is this centripetal force, and how can we quantify it? We know that the formula for centripetal force is derived and developed to be A sub c equals v squared over r, which we're going to skip the derivation and go right to the direct formula. A sub c equals v squared over r. And you can see on the physics reference table that this is formula 18. If we multiply mass times centripetal acceleration, then we get mv squared over r, which is this next formula, which is formula 17. Both of these expressions have an alternative expression, and it's derived as follows. We know that for an average speed, it is the distance divided by time. If the distance around the circle is the circumference, which is 2 pi r, and the time it takes to go around the circle is capital T for period, then the average speed around a circle is also equal to 2 pi r divided by t. And here we have that expression being inserted into the v squared portion of v squared over r. Doing that, we get 2 pi r over t, all of that squared, giving 4 pi squared r over t squared. So you could express centripetal acceleration in terms of the speed or in terms of the time for that given radius. The natural extension to multiply by mass simply puts an m in both of these equations. So you get mv squared over r, or you get 4 pi squared mr over t squared. These two formulas in the red box are for centripetal acceleration and centripetal force, respectively. So what is centrifugal force versus centripetal force? Centripetal force is the force that pulls towards the center, and that is the action force. A centrifugal force is the force that your body feels as it presses against the wall, and the centripetal force is what you feel with the wall pressing against your body if you are in some kind of gravitron amusement park ride. In summary, centripetal force is the force that holds an object moving in a circle. If at any point that force was to cease, so if this was a rock on a string and the string broke, the object would fly straight off along the tangent and it would maintain the speed that it was going, except it would go with a tangential velocity. If this was a car going around a circle and the road friction was keeping it in the turn and you hit a patch of ice, you would go off along the tangent. So whatever the example or the application is, the physical basis for all of the behaviors of objects that move along the tangent are the same, especially when the centripetal force is diminished. We have these two formulas, numbers 17 and 18. In the next video, we're going to talk about how to apply these two formulas and an analysis of variations of different variables in these formulas. I hope you enjoyed the video. Thanks for watching, and we'll see you in the next video.